Hey, what's up, guys? This is Cheng here again. So this time, LeetCode number 1931, painting a grid with 3 different colors. Okay, so you're given like 2 integers, m and n, right? Consider an m times n grid where each cell is initially white, and you can paint each cell with 3 colors, either red, green, or blue, right? And all cells must be painted. And we need to return the number of ways to color the grid with no 2 adjacent cells having the same color, right? For example, if there's only 1 cell, then obviously we have three ways to paint it, right? Then, as you guys can see, the result increased exponentially, right? And the constraints is like this. So keep notice here, m is pretty small, but n is big, right? So that's a description. So this one is like a DP problem. So for this kind of grid, we have some similar problem. I think there's one called paint 3 different grids, or like there's like a happiness people or something like that. Basically similar thing, right? Basically you have a grid, right? And then you will place this cells one by one, right? But there are some constraints when you try to place it. Basically the neighbors can, so for this one it cannot be the same colors. I think for the happiness person, something like, the neighbors cannot be the happiness cannot be greater or smaller than some numbers, but they are essentially the same concept, right? So basically, with like we will need to have like DP, right? So the DP will basically we need to know with the current index, right? So this is the sequence, a card sequence. With the current sequence, we're trying to place this one, but depending on the left neighbor, right? Depending on this one, the left one and the top one, right? So these are the 2 neighbors, because so the reason we only considering the left and top one is because we're always placing this new one, so which means there's nothing on the right side and below, right? So basically we're placing the cells, right? The grid cells one by one from top left to bottom right. That's why every time when we place the current one, we only need to consider the left neighbor and the above neighbor, right? So now, as you guys can see, right, in order for us to place this one, we need to know what's the color on the left side and what's the color on the right side, right? So that's why besides the sequence, we need a second parameter here. And how can we store that, right? We have this grid, right? So let's say here are all the things we have already placed, and now we're trying to place this one, right? So it turns out, all we need to maintain is the previous is the last. Let's say this is m, right? This is n. Okay. It turns out, all we need to maintain is the last m numbers, the last m cells we have placed so far. So the reason being is that, let's say we have a last row. Okay. So the last row has a size of m. Okay. And so the one on the left, let's say this one has the column index j, right? So the left one is what? The left one is the last row of j minus 1, right? Assuming we have this kind of last row index here, right? Right. So this is the one. This is a last row. This is m, right? Let's say this is we're currently at here. Okay. Sorry, we're currently at here. As you guys can see, the left one is the last row j minus 1, right? How about the top one, the above one? The above one is simply the last row of j, right? Because they have the same one. That's how we get the 2 neighbors, right? And after that, based on these two neighbors, different based on different colors. This one could be red, green, red, yellow, right? And we have some different options here, right? Basically, it means that we can paint this cell with certain colors. And after that, right, after this one is done, we also need to update the last row, right? So how do we update it? I mean, assuming we're simply using a list here, we simply just update the last row J into the new color, right? Into a new color, because after we are placing the number here, after we're placing the a color here, uh, this one will become to the new one. Basically, when we try to place this one again, this one will become to the left neighbor, right? And when we reach to here, to the second row here, we are reaching to here, right? And then this one will become to the above one, right? That's why we simply need to update this last row with the current color. That's enough, right? And that's it. I think so. That's the basic solution here, right? I mean, uh, basically we simply need to maintain the last m colors, right? And but since we have m and n, so m is equal within 1 to 5, right? And n is 1 to 1,000. So obviously we want to make n equals to the rows and m equals to columns, because we have this kind of last row list we want to maintain. So the time complexity for this one, or the different combination for this one, is going to be the what? Going to be the 3 to the power of m, right? Because each one of them could have actually it's 4 actually. I think it's 4, because we're gonna use either 3 or 4 basically. I think we can use 0 to represent color, the red, right? 1 blue and 2 green, right? So that's why for each of the cell we have 3 different possible possible values, and we have m, right? So that's going to be 3 power of m. So with this constraint, obviously we want to use m as a column, not the n, right? Okay, so I think that's it, right? I mean, with that we can start coding our DP solution, right? And later on we can improve this one a little bit by using the Bitmask and not this list. Because okay, let's see. So for the DP, right, like I said, sequence, I have a sequence, right, and then I have a m last row. Okay, I call it last row here, and then LRU cache, right, it's none here. So the base case, right, so if the sequence equal to the m times n, right, then we return 1. This one means that, okay, we have successfully painted all the cells, and we have find a valid way, right? Okay, and then for the I and j, right, I is going to be since the sequence is going to be integer, we need to convert it into coordinates, right? It's going to be m, right? J equals to the sequence modular of m, right? So that's the since you're trying to use m as a column, right? That's what we will do here. And so remember, in Python, this you cannot memorize a list or a set. So the only possible way you can do it is by converting this one into a tuple. That's how Python can memorize this value, because this one is a list, right? That's why we have, if we want to use this native, like the row or tuples, we have to do some like trivial tedious conversion, like this one, list last row, we have to convert it from the tuple to a list, right? And then we have answer equal to 0, and then we have to check the neighbors, right? Neighbor colors. I just call it neighbor colors, right? There are different ways. Basically, if the I is greater than 0, right, it means that we need to check the above one, right? So colors dot add, right? It's going to be the last above one is the last row list dot j, right? And then if the j is greater than 0, then we need to check the left one, right? So so similarly for this one, we have the left, which is j minus 1, right? Left neighbor. Okay, cool. So and then for C in range 0, 1, and 2, okay, I just use 0, 1, 2 to represent these three colors, right? So if C not in colors, right, and then I do basically we have to update. We have to update this list and then pass it on. I think I just do a copy here. This. I know this one is not very performant, but I'm just using this one to pass the test case. So like I said, every time when we have decided to paint this current color, we have to update this the last row, right? And then we have answer dot this dp of sequence plus 1, and then we have to convert it to a tuple, right? That's how Python can memorize this list. Okay, and then don't forget to do a modular, right? Mod, okay, I think mod plus 7, right? And then we simply return a dp of 0 dot tuple, right? Let's keep it 0 for everything, right? So this one, I think 0 doesn't really matter, because every time, when we check these numbers, the previous one must have already been set. So you can use 1, 2, 3, or I think 0 doesn't hurt, even at the beginning, it's fine because every time we check the neighbors, the both above one and the left neighbors, they both have already been set, so it's fine. Yeah, I think that's it, right? So if I run this one, oh, did I? Oh, neighbor colors. Okay. Yeah. Okay. I think I use 5 to do the testing. Oops. Wait a second. Index out of range. Let me see what's going on here. Oh, here it should be M instead of N, right? All right, cool. So passed, right? Actually, this one surprisingly it's faster than I expected. Okay. Right. So the time complexity, right? So we have a sequence, right? So the sequence is what? Sequence is like M times N, right? So that's the sequence, and then we have what? We have last row. So the last row is like what? Is the is 3 to the power of M, right? So that's the total number of state. And then within the state, we have, so this one is like constant, right? Only 3. But this one, this part is a little bit tedious, but still, right? This one is only a list because the length of this one is pretty small. So we just need to times another M here, right? So that's the time complexity for this problem, for this solution here, right? Because we have to convert it to list and then convert it back, right, to this one. So that's the total time complexity. And there's another way you can do it. Basically, we just instead of this list, we can simply use like a single integer to represent basically a bit mask to represent those colors. But the issue with bit mask is that uh, we have three values, not two. If there's only two values, we can simply use 0 or 1 to represent, right? But we have three values, so which means we have to use two bits to represent that value. So bear it 0 0 equals to red, maybe 0 1 equals to green. I don't know, doesn't really matter. 1 0 equals to blue, right? Something like this. So and then the bit manipulation will be a little bit tricky, but let's try it, right? So similar idea, right? So before we were using like a list, right, to represent the colors, right, and then we update that. But now we use 2 bits to represent each colors, and then we have to do some bit manipulation to be able to get the bit value and set the bit value. Basically, when we get the two bit values, and when we set, we also set the 2 bits value, right? So let's see how we can do it, right? I mean, so now the last row will be the bit mask instead of a list, right? Let's see what we need to change. Okay. So first one is that how can we get the value, the bit value? So let's say we have 0 1 1 0 and 0 1, right? Or another 1 0. So we have 4 cells here. Basically, you remember we have 2 bits representing each color, each cell, right? So basically the index. So let's say the index we pass in is 1, right? So which means we're trying to get this value, right? And how can we get that? So what we need to do is that we have to basically we're gonna do a right shift for this one by basically we have a mask, right? So the mask shift right shift what? Right shift 2 times I. So after this one, what we will have? We'll have 0 1 1 0 and 0 1, right? So this 2 is gone because we right shifted it out, right? And now we need to get this 2, right? How do we get it? So we simply do this. We simply do a AND with 3, because 3 is 1 1, right? So which means we are going to do a AND with this 0 0 0 0 and 1 1, right? So after this one, what we will have? We'll have like 0 0 0 0 0 1, right? That's exactly what we need for this one, right? So that's how we get the value from this. It's not that too difficult, right? But the tricky part is what? The tricky part is the how can we set the value, right? Let's say if we want to set the value for let's say if we want to try to set the value from 0 1 to 1 0, right? If we try to set this one to 1 0, right? Uh, I don't think there's a straightforward way of doing this, because we simply cannot do an OR, right? We cannot do a mask uh, of do a OR with this 1 0 0 0, because as you guys can see, if we do a OR here, what's gonna happen? This one will, instead of 1 0, it will become to 1 and 1, which is wrong, right? And we cannot even we also cannot do a AND or XOR, right? So then what can we do, right? I mean, there's a workaround, right? We simply just remove this one from the beast mask, and then we add the new one back, right? So what's gonna happen? So we just do a 1 0 1 0 0 1 1 0, right? We do we subtract what? We subtract 0 1 0 0, right? So when I say subtract, I mean the XOR, right? So after this one, what do we have? We'll have 0 1 1 0 0 0 1 0, right? And then we do what? And then we do we add it. We add this new one back, which is 1 0 0 0, right? So when I say add, this is gonna be an OR, right? So now we have 1 0 1 1 0 1 0 and 1 0, right? This is at least this is my workaround of updating these two values. Yep, cool. So that's it, and let's do it then. So now this one is like the Bitmask. We don't need this one. Uh, uh, and here, let's get the value, right? So this value is gonna be what? So the right color is gonna be okay, how about we create the helper functions here, right? Since we're getting this one multiple times, let's create a helper function. Let's get get color, right? Or get beat. Let's get color. So first one is the mask, right? Second one is the index, right? So for this one, we returned what? We, like I said, we return the mask. We do a right shift, right, to 2 times the index, right, and then we do a end of 3, right? I think I need another parenthesis here. Okay. So that's it. And then here, I just need to do a get color, right? And it's going to be a last row of J, right? Similarly for this one, I do this, right? J minus 1. Okay. And here, we don't need this tedious conversion anymore, but we need to set the value, right? Let's so to set the values, what do we have? Remember, we need the you know what? Let's create another helper function. It's called set color. We have the mask, we have the index, and we have the new color, right? We want to set. So for this one, like I said, we have to do some we need to do some workaround here. So first, we will need to subtract the that old value from this one. So that's why I'm going to call it old color, right? Luckily, we already defined it, right? So we need to get the old value, old color for this index, which is the mask dot index, right? And then you return the mask XOR. So this is equivalent to the subtract, right? Gonna old color do a left shift of 2 times index, right? Because we have to move this one to the right position, right? And then we have after this one, we're gonna add the new one back, which is the new color, right? So we simply just copy and paste this one. Now we have a new color, right? So add means or, right? And that's how we do update the mask. And so here, set color, and we have a last row. We have the index is J, the new color is C, right? Now we don't need to do this tuple thing. All we need is a 0. Okay. And I think that's it, right? So if I run the code, okay, accept it. Let's try it again. Yeah, cool. But this one is surprisingly, this one is slower than than the list one. I don't know. I don't know why. I was thinking that the bit manipulation should be faster than the list manipulation. but for some reason it's even slower. But anyway, right? Anyway, so that's the that's it for this problem, I guess, and I'll stop here then. Cool, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.